So Thomson found that these negative electrons were in the atom. And so then, where are they? What are they doing? How is this all arranged together? So his idea was that these electrons are just kind of randomly distributed in some sort of positively charged sphere. Because we knew that atoms didn't have charges, but the electron had a charge. So there must be positive charge in there somewhere that's balancing the negative charge. And so this became known as the Plum Pudding model. Now, have any of you ever had plum pudding? Anybody? I haven't either. It's an English dessert, and it just doesn't sound very good, does it? Plum pudding? It's really not even a pudding. The closest thing we have would be a blueberry muffin. Do you know what a blueberry muffin is? Right? So you've got this muffin, and it's got chunks of, the blueberries distributed through it. So the positive sphere is like the muffin part, and the electrons are like the blueberries, and they're just kind of dotted throughout. And this was his idea of what the model was like, what the atom was like. So this is a model. He's saying this is what it is. Now we know that this was not correct, but you have to start somewhere. So Ernest Rutherford in 1909, I'm not going to quiz you on these dates either, he actually was a student of Thomson, and he believed in this plum pudding model, and he set out to do some experiments and test this model, and his goal was to confirm that the model was correct. So what he did is he took a stream of positively charged particles and shot them at a very, very thin sheet of gold foil. So here's an illustration of his setup. So here he has this source of positive particles. They were actually helium nuclei. He shoots them through here at this piece of gold foil, and then he has a detector set up around it so that they could see where these particles went. And what happened is that most of the particles went straight through. Some of them were deflected at small angles, and a few were deflected at large angles. This was a very unexpected result. Approximately 1 in 20,000 particles bounced back. And the way he explained this was, he said it was as surprising as if you took a cannonball and shot it at a piece of tissue paper, and it bounced off the tissue paper and hit you in the face. Right? A cannonball should not bounce off tissue paper. It should go straight through. But these particles bounced back. They did not expect that. Because in this plum pudding model, these particles, these electron particles, are very, very small. And so they were expecting most of the positive particles to just go straight through. They were not expecting them to bounce back. But they bounced back. And so because of this, the plum pudding model couldn't be correct. The predicted result was that the alpha particles would go straight through, but what actually happened is some of them bounced back. So this led to a new model. He concluded that matter must not be as uniform as it appears. There must be a lot of empty space and small regions of very dense matter. And so the nuclear model holds that there is a nucleus consisting of the protons and neutrons that's in the center of the atom, and there are electrons around, but they are very, very tiny, and most of this is empty space. That's why most of the alpha particles went straight through. The reason that some bounced back were because they hit the nucleus. The nucleus is incredibly massive. If you were able to take nuclei and compact them into the size of a period on a printed piece of paper, it would weigh, I think it was 100 million tons. The size of a period. Just the nucleus. Nuclei, that big. It's mind-bogglingly dense. Because most of matter, we look at the bench top, and it seems really solid, doesn't it? You could bang your elbow on that and get a nice bruise. It's mostly empty space. The nucleus in the center is very small. If the nucleus was the size of a green pea and you put it on the 50-yard line, the edge of the atom would be at the end zones. And floating around in there would be a few electrons that are almost 2,000 times smaller than the particles in the nucleus. It's mostly empty space. Just kind of think about it and try to get your mind around that. So, based on his idea, he proposed the nuclear theory of the atom. Most of the atom's mass and all of its positive charge is contained in a small core called the nucleus. Most of the volume of the atom is empty space, and in that empty space we have tiny negatively charged electrons that are dispersed. He's not saying anything about what those electrons are doing. Another important part of this is that there are as many negatively charged electrons outside the nucleus as there are positively charged particles inside the nucleus. So the atom is electrically neutral. The positive particles are the protons. Protons are positive. They both start with P. This model was highly successful, but it was still incomplete. There was mass that was unaccounted for. And what they figured out later, Rutherford and one of his students, James Chadwick, who died in 1974. Wow. I was actually alive in 1974. I could have met him and I missed out. Wow. They figured out that the unaccounted for mass was due to neutrons. So there are not just protons in the nucleus, but there's another particle. It's called a neutron, and it's neutral. Okay? Neutrons are neutral, protons are positive. That leaves the electrons to be negative. So we've got the neutrons and the protons in the nucleus. Neutrons are neutral, no electrical charge. The mass of the neutron is similar to that of a proton. So they're about the same size. And for our purposes, we can consider them to be the same size. If we look at a hydrogen atom contains only one proton and no neutrons. So it's got one proton, one electron, no neutrons. But if we look at the helium atom, a helium atom is 4 times as massive as a hydrogen atom. The number of protons don't account for that, but it has 2 protons and 2 neutrons, and the neutrons are essentially equal to the protons in mass. So it has 4 massive particles. The hydrogen atom only has 1. And so this explained the observed differences in the masses of the elements.